Welcome back, Bulldogs. We are going to continue on in Chapter 3 today. And the first thing we're going to do is we're going to take a look back at problem 3.5 that you did yesterday for your homework. In this problem, you took a triangle and you enlarged it and took a look at the lengths of certain sides. And we're going to use that problem to kick off our lesson today. And the main focus of our lesson is similarity or similar figures. We're going to be taking a look at how scale factor affects similar figures, how side lengths change, what happens with angle measures, and how do we identify if figures are similar. So we'll talk about all of those things, and we'll wrap up today with some practice for you guys. All right, so let's get started. As I mentioned before, problem 3-5 was one of your homework problems from the last lesson video. And in this problem, it first asks you, what are the side lengths of the original triangle ABC? So you had to plot some points. A was the point 0, 0. B was the point 3, 4. C was the point 3, 0. And to figure out the side length, some of these we can just count. Like from A to C, that's 3 units. From C to B, that's 4 units. And if you were to use Pythagorean theorem here, 3 squared plus 4 squared would equal C squared. So if you go ahead and solve this, 9 plus 16 is equal to C squared. 25 is equal to C squared. So that third length is 5. Okay. Then in part B, it wants you to dilate that original figure by a factor of 2. Okay. So remember, dilations happen along these projection lines. And here is our center. We're dilating it from the origin. And so our projection lines start at the center of dilation. They move out through a point on the original triangle and continue on until we get to a point on the new triangle. Now, in the original triangle, AC is 3 units long, so that means A to C prime should be 6 units long, okay? And if we take a look at A to B, since that's a diagonal line, we can use slope triangles, okay? Remember that method from our last lesson. Since we're dilating it by a factor of 2, that means we want to move through 2 slope triangles. Now, the first one is already there. That's for the original figure. If I draw in another slope triangle right here, this is where B prime should be. Okay, so we'll continue that out. And here is my new triangle, C prime, B prime. Any point on the center of dilation is going to stay put during the dilation. And so there is my new triangle, okay? And it wants me to find the area and perimeter of my new triangle. Well, that would mean I'm finding the lengths of the sides, okay? So from A to C prime, that's 6 units long, and that's what's expected because the original side length was 3 and I doubled it. From B to B prime, from C prime to B prime, it's going to be 8 units long. And again, that's what I expected because originally it was 4 units long. Now from A to B prime, we could use Pythagorean theorem again, 6 and 8, square both of those and figure out what AB prime is, but we could also use the fact that from A to B is 5, and if I double that, that means the entire length here is 10 units long. So you can easily figure out the perimeter. 6 plus 8 is 14, plus 10 is 24. Or you could figure out the area, which is 1/2 the base, 6, times the height, 8, which is 24 square units. Now we're going to use that same triangle to help us learn a little bit about similarity, okay? And we're going to start with an idea called corresponding sides. You'll notice in problem 3-11, I have a figure over here, okay? And that is just the original triangle and the enlargement from problem 3-5, all right? And the first couple questions ask about these things called corresponding sides. And corresponding sides are sides between two figures that match up together. So it's the pre-image side and the image side. Those would be corresponding sides. So the first question asks, what side corresponds to side CB? Well, in the larger triangle, that would be side C prime, B prime. And which side corresponds to side AB? Well, that would be side A prime, B prime. The second question asks, what is the relationship between the sides in triangle ABC and their corresponding sides in A prime, B prime, C prime? Well, in problem 3-5, the dilation used a scale factor of 2. So if the scale factor is equal to 2, then every side in ABC is going to be doubled to get the length of the side in A prime, B prime, C prime. So the larger triangle with sides are double what they are in the smaller triangle. Why do segments AB and A prime, B prime lie on the same line, and also segments AC and A prime, C prime? Well, that's because they start from that center of dilation, okay? One endpoint of those segments is the center of dilation. And finally, why does segment BC not lie on segment B prime, C prime? Because none of the points of that segment are the center of dilation. Now let's take a look at the relationship between the side lengths. Could we add the same number to each side of triangle ABC to get the lengths in A prime, B prime, C prime? Well, I wrote in those lengths for us, and let's take a look at the lengths in triangle ABC, 3, 4, and 5. To go from 3 to 6, I have to add 3. If I take 4 and add 3 to it, I don't get 8. If I take 5 and add 3 to it, I don't get 10. So simply adding the same number to each side length will not produce the lengths of the new triangle after the dilation. What needs to happen is we need to use the scale factor and multiply each of the side lengths in the original triangle by that scale factor to produce the new side lengths in the new triangle. And that scale factor in this case is 2. 3 times 2 gives us 6, 4 times 2 gives us 8, and 5 times 2 gives us 10. Now, what if we form a new triangle, triangle A double prime, B double prime, C double prime, and the length of segment A double prime, B double prime is 20 units long? What scale factor was used, and how do we know? Well, originally, side AB is 5 units long. That's this one right here. So if we're dilating that from 5 to a side length that's 20, we have to think about what that scale factor is that was used. 5 times what number? K. Remember in our Desmos dilations lesson, we used K to represent that scale factor. So 5 times K is equal to 20. That means K would equal 4. So our scale factor would be 4. Let's take a minute and summarize some of the things that we've learned so far about dilations and similarity. So dilations change the shape of a figure, but not its size. Side lengths will change, but angle measures stay the same. And dilations produce something called similar figures. Similar figures are figures that are the same shape but different sizes, and they are connected by a certain scale factor. The scale factor, or sometimes called the zoom factor, is the number that is used to multiply all of the side lengths in the original figure to produce the side lengths in the new figure. So this is how much we are enlarging the figure by. Now, if you take a look at the pictures here of the dog, okay, there's an original picture where it's showing the height of the dog's head is 5, and the new picture showing that the height of the dog's head is 15. So if we enlarged the picture of that dog from 5 to 15, what's the scale factor? We're multiplying each dimension in the original dog by 3. Remember that in our Desmos activity, we learned that when a scale factor is bigger than 1, we are enlarging the figure, so we're making it bigger. And when the scale factor is equal to 1, the figure stays the same size. And when the scale factor is between 0 and 1, we are reducing the size of the original figure. When the scale factor is equal to 1, the dilation actually produces congruent figures. This means that the preimage and the image are the same size and shape. When we compare the lengths of the sides between two similar figures, we get something called the ratio of similarity. Remember, a ratio is just a fraction where we compare two quantities. So when we make this comparison between the side lengths and similar figures, we can either compare side lengths between the two figures, meaning we choose one length in one of the figures and compare it to its corresponding length in the other figure. So comparing the heights, notice they're taking the height in the larger figure and comparing it to the height in the smaller figure. And we can do the same thing with the widths, okay? We can compare the width in the larger figure to the width in the smaller figure. We're going between those two figures. We pick a length from one and compare it to its corresponding length in the other. And when we do that, we need to make sure we always set up our ratios the same way. We are comparing the big or the larger figure to the smaller one, and all of our ratios are set up that way. So we can reduce these ratios of similarity. Even though they look different, 24 over 8 reduces to 3, and 18 over 6 also reduces to 3. We can also compare the lengths within the same figure. Okay, so for example, we can take a look at comparing the 8 to the 6, the larger side to the smaller side. So we can make a comparison here, 8 over 6, and do the same thing between these two figures, large to small, 24 to 18. Notice though how I'm using that same comparison throughout. I'm always comparing the large side within a figure to the smaller side given within that same figure. And again, our ratios of similarity should reduce to the same number. 8 over 6 reduces to 4 over 3. And 24 over 18 also reduces to 4 over 3. 24 and 18 are both divisible by 6. And this is a test to let us know if these figures actually are similar or not, because if you set up ratios between the sides and they don't reduce to the same number every time, then you know that your figures aren't similar. Now, how can we use this idea to help us find x in part C? Well, we're going to create comparisons, and since we know those ratios of similarity should be equal to each other, because it doesn't matter which pair of corresponding sides I compare to each other, we can then set those ratios of similarity equal to each other and solve a proportion. I'm going to do this two ways. Okay, the first way, I'm going to compare between the two figures, and the second way, I'm going to compare within each figure and then set the ratios equal to each other. Comparing between the two figures means I'm going to pick a side in one figure and find its corresponding side in the other figure. For example, 8 and 20. So that's one ratio of similarity I could set up. You could also use the reciprocal of that ratio, 20 over 8. Now, if I started with the small figure and compared it to the large figure, then every other comparison I use has to be set up that same way, which means I need to start with the 6 and compare it to its corresponding side of x. And now I can solve this proportion. Remember, we solve these by cross multiplying. 8 times x is equal to 6 times 20, which is 120. Divide both sides by 8, and x is equal to 15. Now, if we set up our comparisons within the figures, that means I'm comparing two sides in the smaller figure, and then my other ratio has that same comparison but with the corresponding sides in the larger figure. So that might mean I'm comparing 8 to 6, and the comparison with the larger figure then would be 20 to x. Notice 8 and 20 are corresponding sides between the two figures, and they're both in the numerator. 6 and x are also corresponding sides, and they are both in the denominator. Solving this by cross multiplying gives me 8x equals 120, and of course dividing by 8 again gives us x is equal to 15. So either way, I'm getting the same answer for x. Now what I'd like you to do is think about what we talked about today with ratios of similarity and scale factor, and see if you can answer these two questions. Pause the video, write down your responses, and then we'll check our work together. Okay, in the first problem, we are trying to figure out if the triangles are similar. And how do we know? Okay, well, remember, if figures are similar, we're going to look for a common scale factor that connects the side lengths. So if we compare the two larger sides in the triangle and the two medium sides in the triangle and the two largest sides in the triangle, is there a common scale factor that links those lengths together? Well, to start with 3, we'd have to multiply it by 2 to get 6. 4, though, if we multiply it by 2, we do not get 7. But 5, we can multiply by 2 and end up at 10. Even though it works for 2 of the side lengths, because it doesn't work for the third, these triangles are not similar. And in the second figure, it tells you that the figures are similar, and we have to find x and y, which means we're setting up those proportions again, those comparisons between the sides. So solving for x, we need to set up ratios, and at least one of those ratios has to have x in it. So let's take a look. X is right here. Its corresponding side in the other figure is the 11. So I know that one of my ratios has to be x over 11 if I'm comparing between the two figures, okay? And so then what I want to do is set up another comparison between the two figures. Now notice I went from the larger one to the smaller one. So that means my next ratio has to be set up the same way. I'm going to pull a side from the larger figure, 24, and compare it to its corresponding side, 8, in the smaller figure. Why didn't I use 18? Well, because then I'd be using y, and I'd have two variables in the same problem. So we're going to cross multiply here. 8x is equal to 11 times 24. And then if we divide both sides by 8, we'll find out that x is equal to 33. Now for the second part, it wants us to find y. So again, I'm going to set up those ratios. I'm going to compare within the same figure now. So I'm going to erase some of my markings from before. and I'm going to pick side lengths to compare within the figure. So I'm going to choose Y and one of the other side lengths in this smaller figure, maybe the 8. I'll compare Y to 8, and now I just need to make the same comparison with their corresponding sides in the second figure. The side length of Y corresponds to the side length of 18 in the larger figure, and the side length of 8 corresponds to the side length of 24 in the larger figure. Cross multiplying gives us 24y equal to 8 times 18, which is 144. And if we divide both sides by 24, we find that y is equal to 6. So what I'd like you to do now for me is complete the review and preview problems in section 3.1.2 from your textbook. And when you're done with that, take a picture and upload your work into the assignment tab so I can see where you're at with your understanding. Have a great day, and don't hesitate to email me if you have any questions.